Let's get started. I would like first to inform you that today we're hosting our guest from Savannah River National Laboratory. We have three guests. Dr. Glenn Kessinger, which is Non-Proliferation Technology Section Director. David Wilson, which is Associate Laboratory Director for National Security, and James Bollinger, who is a Program Manager. So Dr. Kissinger will present a seminar and make overview of Savannah River National Lab with emphasis on the activities in the area of nuclear non-proliferation. So some facts from his bio. He received PhD in physical chemistry in 1989 from the University of Kansas, where he studied under the direction of Professor Gilles. He has worked as a process development chemistry at Idaho National Laboratory and Savannah River National Laboratory. He joined the Non-Proliferation Technology Section as a manager in 2011 and has been responsible for organization working in the area of nuclear forensic, non-proliferation, technology development, and trace analysis and analytical chemistry. His technical interests include high-temperature chemistry of refractory materials, mass spectrometry, nuclear fuel cycle chemistry. His research and development activity have addressed glass ceramic waste for immobilization of Idaho chemical processing plant, development of naval fuel processing flow sheets, investigation of the physical and chemical phenomena related to thermal ionization, mass spectrometry, ion formation, and processing, characterization, and storage of actinide materials. Please join me in welcoming our speaker.
I'd like to start out by thanking Professor Ivanov for the nice introduction. And for everyone we met today, thank you very much. It's been a really informative day and I've learned a lot. Like he said, what I want to tell you about today are a little bit about the Savannah River National Laboratory, and specifically my interest right now is non-proliferation technology. So first let's start out with what is the Savannah River site. It was a weapons complex facility, and the laboratory is a fuel cycle laboratory that supported these processes. And the historical mission was producing plutonium and producing tritium. The facilities included reactors, chemical separation plants where we processed the targets and fuels that came from the reactors, heavy water extraction. We used the water out of the Savannah River to produce heavy water, nuclear fuel target and fabrication activities. We designed and fabricated the fuel and the targets for the reactors there on site, and the people in the laboratory did the development work on that. Naval fuels, we had a facility on site where we could fabricate and process naval fuel, propulsion fuels, and of course waste management for all of the effluents that came from these processes. And we did tritium recovery, and we are the tritium site for the weapons complex. And then we have, of course, in the laboratory, we had R&D laboratories where we supported the ongoing processes for all of these facilities, as well as developing the baseline processes. And then in each one of the processing facilities, we also had support laboratories running 24 hours a day, 7 days a week, 365 days a year as the processes were running. And so we have the laboratories built on 6 decades of nuclear experience. What do we do today? We have a different mission today. We're still supporting that tritium production mission. We're still doing process development, but it's mostly looking at the immobilization of effluents from the Cold War processing. We still help run the canyon. We did the development work, and we do the process support still for the Defense Waste Processing Facility, where high-level radioactive waste is immobilized into a vitrified glass form. We've also got a lower level waste facility, the salt waste processing facility, where we immobilize material, and we did the development work there and helped do troubleshooting on their technical side. And also they're building waste facilities up in Hanford, and we're doing the technical development support for those as well. Our site is the site of, SRS is the site where surplus weapons plutonium is stored for the US government, and so we support that safe storage at the K Area Material Storage Facility. In the nuclear non-proliferation business, which I'm going to talk more about later, we're still doing some plutonium processing, and we also in the laboratory we're involved in supporting the intelligence community of the government. So what is the laboratory at the glance, and what do we do? Essentially, we try to protect the nation by using science and engineering to solve problems. Our competencies, not surprisingly, are in the environmental area, tritium processing, nuclear materials processing and dispositioning, and then nuclear detection, characterization, and assessments. We have about 1,000 staff members, a budget of about $365 million, and our program areas are, even though we're EM's laboratory, most of the largest amount of our work is in the national security area, and nuclear materials management also is part of national security. So almost 60% of the laboratory's budget is addressing national security issues. We also have a growing program in energy and manufacturing, along with that environmental stewardship support. We have facilities to address all kinds of materials, ranging from non-radioactive materials, where we've got just normal laboratories, both on-site, and we have off-site labs that we lease. For highly radioactive materials, such as irradiated fuel, we have a bank of shielded cells. We have intermediate level cells that are connected to glove boxes that allow us to do separations in the cells and bring materials out directly to the glove boxes. And then we also have radiological hoods for materials such as uranium that are low activity. Now, in the non-proliferation business that I'm primarily interested in, we have two programmatic aspects. The first has to do with materials and control of materials. Like I said, we're the repository for all the surplus U.S. weapons grade material in the complex. Also, along with that, we're responsible for programs that are aimed at reducing the proliferation risks of materials worldwide. And one of the ways we do this is we have operationally built a mobile plutonium facility, which is a set of sealand containers that couple together that allow us to introduce material to it, package it appropriately for shipment, and then also for material return from foreign countries to the U.S. that we coordinate a lot of that work. The other thing we do, and this is the part of the business that I'm mostly interested in, is the detection of proliferation activities. So on that nuclear materials management side, we've got a couple of really interesting things that we're working on right now. One is we're recovering plutonium-244 from targets. Back during the 1930s, a set of high 242 to high plutonium-242 targets, and those have been cooling in our storage basins for a number of years, and we pretty much have the nation's inventory of plutonium-244 in these, and we've developed a process that we're going to introduce into the shielded cells facility that we're in the process of assembling the equipment now, where we're going to recover the plutonium from these targets, and then it's going to ultimately get separated out to recover the 244. The other thing we're doing is for high assay, low enriched uranium for reactors, we've been evaluating the use of H-canyon for downblending material for these kinds of uses. Now on this other portion of the thing we're doing here on the management regarding dispositioning, as well as this mobile plutonium facility we have here, which is shown during one of their deployments. This facility has been deployed north of the Arctic Circle during the winter, during the summer at the Nevada test site, and then their third deployment was Key West during the summer. That was supposed to be subtropical. I think that was a vacation for the folks. And this is when they were down at Key West at the naval facility. We're constantly trying to improve our processes. We've come up with what we call the MPF Lite, where we are going to decrease the footprint and increase the throughput. The other things we're doing is we're going back and looking at some old technology, such as electrolytic dissolution for recovering plutonium from foreign origin fast critical assemblies. And we're also have been working on graphite fuel, where we've received some pebble bed fuel from Germany, and we've developed a chemical process to digest that material so that we can recover the fissile material from it. And lastly, as well as this national security aspect, our nuclear materials technology people support the EM activities, because the Environmental Management Organization of DOE has thousands of to be determined processing items that we don't really know what to do with. So what's the history of our non-proliferation technology program? This is interesting. The site was originated in the early 1950s, and DuPont was running the site and designed the facilities. And the first thing they did was a baseline environmental assessment of the entire site before they ever started operating. And then over the years, they did constant environmental monitoring. And so the organization that Jim and I are in originated as this site environmental monitoring group. And so folks in our organization developed sampling techniques and the analyses that were necessary to demonstrate the performance of our processes. And these, of course, included those nuclear material processing facilities. And then as regulatory compliance became more important, we produced information that was necessary to show we were meeting the environmental regulations. This included ability to detect materials at distance. This allowed us then, during above ground testing, to actually detect fallout. Along with this organization of environmental monitoring, we also have an atmospheric technologies organization that's embedded in our section. And the folks do transport work, and they also support all of our site emergency services. We use all these capabilities to support both our on-site and off-site customers. And on our collections and analysis type work, we do the research, the development and deployment of the technologies, and we can collect solids, liquids, gases, organic matter. We can do trace analysis on most radionuclides and other things in the environment which would be of interest. And the other thing we do is we go ahead and we know how to interpret data and do source calculations. So our capabilities are primarily in the areas of collections and analysis, and that is our nuclear non-proliferation work is in the area of signatures, and I'll say a little bit about what signatures are. Nuclear forensics R&D, atmospheric and hydrologic technology that we use to support our emergency response activities and also support our field work. And lastly, we have a connection to law enforcement. We host the FBI's Radiological Evidence Examination Facility. So what are signatures? A signature is essentially a property that helps us understand the provenance of some material that we collect. And so, as you can imagine, signatures have a variety of types. For such as an explosion, a prompt signature would be the electromagnetic pulse, gamma emission, a seismic discharge. We also isotope ratios of materials that we collect. Anthropogenic materials generally have a different isotope ratio in the actinides than naturally occurring. There are trace materials of both elements and compounds that come from specific proliferation activities that you wouldn't find in the environment. Maybe the morphology of what you're collecting also might be different than what you would expect in the naturally occurring case. And lastly, you can use these things to do decay dating. Now, nuclear forensics, which is a good portion of our business, means a lot of things to a lot of different people. In our portion of the business, it's collection, characterization, analysis, and evaluation of material samples, things that you find that might result from the illicit use or intended use of radiological or nuclear material. DITRA views it as primarily as the ability to identify the source of material from debris that they would collect. The IAEA is interested in intercepted nuclear material or radioactive material that they find and identifying its origin. And lastly, DNDO says that this is the keystone of nuclear security. So we do a lot of in-field collections, particles, gases, biota. The platforms we collect from, we've been out on the ocean and on lakes and ships, all-terrain vehicles. We have people that maybe carry around a backpack with a sniffer on their back, robotic equipment, and airborne systems, and two of the airborne systems are here. We've deployed particle collectors and other collectors and detection devices on drones. During some above ground high explosive tests, we developed model rockets with particle collectors in the nose cone that were flown through the plume of the blast to understand what the composition and morphology of the material that was being ejected from the blast was. This is one of our mobile laboratory where we had both counting equipment and at various times have had gas chromatographs on it. And these are a couple of our collection devices. Now, our analytical capabilities are pretty extensive, we think. We have world-class sensitivity for multiple materials of interest to us, which would be tritium, noble gases, and a range of radionuclides. And the ways we do this is we have high sensitivity mass spectrometers, we have CMs, we do X-ray diffraction, we've got a spectroscopic group, and we also really exceptional skills in low-level counting. Okay, that's right. Sort of our workhorse mass spectrometer probably is older than most of the people in this room. This instrument was built in the 1970s by one of my predecessors, and the electronics have been upgraded on it 3 times during that time. It's a 3-stage thermal ionization mass spectrometer. It's located in a class 10,000 clean room. Detection limits are down in the low femtograms. in the level of quantification down to tens of femtograms. We also have high-resolution ICP-MS with a multi-collector system that allows us to simultaneously detect the actinides located in that same class 10,000 clean room area. And one might wonder, why do you have two of these? Well, TIMS is really good for plutonium, and ICP-MS is really good for uranium, and ICP-MS you would prefer to use when you can because the sample preparation is probably less than half as much effort. However, it doesn't work well for plutonium because you can get some interferences, especially on plutonium-239. You can in your ICP signal, you can get uranium-238 plus 1, which makes 239, and so that causes sort of a problem. In our scanning microscopy lab, we have two instruments. Our workhorse instrument is this small one over here. It's an Aspects instrument. That's our triage instrument. It can search a planchette, automated searching of planchettes. Like we'll put like a 2x2 silicon wafer in there that has collected samples, and it can look at it, and for the elements of interest, it can map the surface, tell you where the elements of interest are. Then we take it over to our higher resolution Zeiss instrument and look at the particular particles that we're interested in. We also, as well as this class 10,000 clean room area, we have access to highly contaminated areas. This is an experiment that was being done in the Shield. And these are two of the instruments that we have for contaminated samples. And the reason I show these to you is because there's some innovations associated with working in the radiological field that you don't have to in non-rad. And that is, what you see here is the business end of these instruments are located in a hood or a glove box with the electronics outside. And so this takes some extra design and effort on the front end and planning. As I said, we have an atmospheric technologies organization in our section for supporting our program, and they use models that they've developed and purchased to understand and predict the transport of materials. These are two aspects, as I said earlier. For our site support, they support our comprehensive meteorological monitoring program. They support the emergency response both for the site and for other things that might happen. There was a chemical release during a train accident near the site a few years ago, and they did the modeling on that to understand where the plume would be going. And then lastly, they support our regulatory activities for our air permits and our safety analyses. They also form an important support for our non-proliferation work. And that is, we develop these technologies and we have to go out into the field and test them. And so you don't know how well your equipment works unless you test it. And so we'll go out on a field exercise, and these folks will go with our collector folks, and they'll tell them, well, the atmospheric prediction is the wind's coming from the southwest, so you want to be northwest of the location where the emission will be taking place. And so it allows us to come up with sampling plans. They also are able to help predict and interpret what we see. You can go back and look at the meteorological situation for the days when you were doing your work to verify that what we think happened really happened. And here's one of the things they worked on was when Fukushima happened, they immediately went to work looking at where the plume was so that people would know where to go out and collect samples, and they did, and they supported our response effort there. Probably our underground counting facility is our crown jewel. And this facility was fabricated, was built in the early 1980s. The counting room is fabricated from pre-World War II steel armor from the USS Antietam. It's 48 feet below grade. That's 30 meters of water equivalent. It's capped with borated concrete, and around it is packed specular hematite to filter cosmic rays. Our minimum detectable activities on 3-day counts run down in the tenths to hundredths of picocuries, and the best measurement we've ever made, the lowest level measurement, is 39 minus 12 femtograms. Now, as far as our programmatic support goes, we've got a variety of ongoing programs with sponsors. We support the government intelligence community. One of our major sponsors is Defense Nuclear Non-Proliferation R&D, also known as NA-22. In FY19, we had 17 ongoing projects, primarily through the Office of Proliferation Detection. We had 7 new starts coming into this year, and this includes participation in 2 university consortia projects, one with the University of Michigan and one with Georgia Tech. On the DoD side, we have 2 new programs that are just starting up. One is a reach-back program where we'll provide 24-hour-a-day, 7-day-a-week, 365 days a year support for them if they have technical field questions that come from warfighters out in the field. And the other one is we're trying to initiate work on a test bed. We're initiating work on a test bed for field testing of equipment. The program sponsors we have here include the FBI, as I'd said earlier, NNSA, the Department of Homeland Security, DITRA, and the intelligence community. As I said earlier, Savannah Riverside is home to the Tritium Production facility. We're experts in measuring tritium at all levels, and we routinely analyze tritium that's collected from the air as an oxide, for example. Tritiated water, we extract it from atmospheric gas. We crack it using magnesium to form hydrogen, and then we count it. We can also do the elemental form. We have developed techniques to collect it, and we have a process for recovering the methane, tritiated methane as well. We are able to analyze that, and we do all of this counting in gas proportional counters, and the electronics and the detectors and everything are built in-house by our staff who design them and fabricate them. I'd also said that we're the hub lab for the FBI. If during an investigation, FBI folks recover material they believe to be radioactively contaminated, they will send it to us. We have staff on hand to support them. Essentially, the way it works is they'll bring us the samples. We will start out by doing like an initial assay of the material to determine what the level of radioactivity is. And then we will set up the parameters for them to perform their traditional forensic analyses, such as fingerprinting analysis, DNA, in a rat environment that could range from being in a hood to a glove bag to a glove box, depending on the radiolytic conditions. We provide a scientist that does all of the coordination with our health physics people to ensure the smooth operations. If they see some radioactive material on these things that they would like analyzed, or if they want any of chemical analyses done on these materials, we have a ISO 17025 accredited chemical analysis program where we have 13 different methods that we use that range from trace processes that we would perform in our class 10,000 clean room, all the way up to highly radioactive samples as well, to support them. And here are just some examples of some of the instrumentation we used. This was an insert for the shielded cells that we developed for our support work with them. And here are a couple of the instruments that we use. Now, I've talked a lot about applied work and customers. That's not all we do. We're also interested in fundamental science in the laboratory. So we have a laboratory-directed research and development program. And the way we fund that is we tax all of our external programs 5%, and we distribute the money based on a competitive proposal process. Our focus areas are environmental stewardship, nuclear materials management, national security, our energy manufacturing business, as well as we have cross-cutting capabilities in process imaging and cybersecurity that we've been funding. And you can see that this is sort of what the breakdown was last year of the funding profile, about 50% for national security and the rest of the laboratory carrying up the rest. In FY20, we had 12 continuation projects. We had 15 new starts. And this year we started a new discovery science program where we had 3 new starts, where instead of, in the past, these have been very applied programs where we had specific science problems we were looking for that were related to our ongoing businesses. In this discovery science program, these are high risk, high reward situations that we realize may not come to fruition, but if you hit on 1 out of 10 of them, you've probably hit a home run. And so we have 3 of those that are starting up this year, and folks from national security are involved in 2 of them. And just to sort of give you a little heads up here on our work in the non-proliferation world, even when you're doing work for customers, you can also still publish and do basic science. And one of the things that we've used our interest in uranium to study is the behavior of uranium tetrafluoride in the environment. Uranium fluorides are important signatures in the uranium processing cycle, and it's been understood for a long time that when that kind of material escapes out into the environment, it doesn't stay as a fluoride very long. It transforms into other things, but no one had really ever nailed down exactly how the transformation took place. And so we used our capabilities in X-ray diffraction, where we have an X-ray diffractometer with a humidity and temperature control stage that allowed us to vary the humidity of fluorides while we were over them at various temperatures, while we were taking the diffraction patterns to see the ingrowth of these degradation phases. And then once we thought we understood where this was happening, we then went to our laser Raman system, which is also equipped with an atmosphere control stage, and we actually varied the atmosphere relative humidity over a period of days and did a variety of experiments. And here at 50% relative humidity, you can see that you start out on day 1 with uranium fluorides, and by the time you get to about day 7, you can see the oxides starting to grow in. We were able to conclude that the most likely pathway is a 2-step process where you get an intermediate of uranyl fluoride, where the uranium-4 becomes a uranium-6 oxidation state, and then if it's around the moisture long enough, it'll essentially convert entirely into the hydroxide. And this has really helped us in our understanding of the environmental uranium chemistry. So at this point, I want to say a few words about the future. I've told you where we were and what we're doing now. And the question probably most of you in this room are wondering is, where are you going? Well, I was hired during the Cold War. And the Cold War is long since over. and most of us are at retirement age. And so we've been losing staff to retirement at about the rate of 10% a year for the last few years. Up until my mid-50s, from the time I was about 30 on, I was within 1 or 2 years of the mean age of the workforce where I was working. Well, I'm now in my early 60s, and the mean age is now down to 47, because you can see from this distribution that we've got a bimodal distribution, and we are hiring a lot of people, and there's a lot of us that are about ready to depart. And so in the future, I think what we're going to see is we're going to be transitioning to doing more basic science work. And one of the things that we've done over the last few years is we've taken an increased concentration on employee onboarding, training, and mentoring. And lastly, as part of that, we're strengthening our university intern and postdoc programs. Last summer, we were up to 46 interns for the summer. We're enhancing our graduate student opportunities, and we're increasing our focus on our postdoc program in the coming years, that we're growing that program rapidly. So I guess at this point I'll go ahead and summarize. What I'd like you to take away from this is we're a multi-program laboratory. We're sponsored by EM, but half of our work is supported by national security programs. We have hallmark programs in fuel cycle science and engineering. These programs across all of our directorates. We are supporting the last full-scale nuclear processing facility for irradiated materials in the complex. We're heavily involved in supporting environmental remediation activities across the entire complex. And in the national security business, we've been doing non-proliferation for 60-plus years. We're the hub lab for the FBI, and we're continuing to support our weapons programs. And I guess at this point, I'll go ahead and stop and see if anyone has any questions.
So, questions, comments?
I was expecting to hear something about the Californium-242, but you didn't mention anything about.
Oh, I think that's probably outside my area of expertise.
Yeah, but it's coming from the target in the.
It's going to come from the plutonium. Well, I'm a plutonium chemist. Oh yes, plutonium-244 is not the only thing that's going to get recovered.
Right.
And essentially, I was involved a little bit in the process development on this. But essentially, there's going to be the plutonium and there's going to be the other stuff. And we're not actually going to do the separations on those. I believe all that material is going up to Oak Ridge, and they're actually going to be doing the separations on that. Okay. Yes, sir.
I'll ask you a plutonium question then.
Okay.
What's the interest in 244?
The interest in 244 is 244 is very long half-lived, which means that you can use it in tracer experiments, and its biological damage is not going to be nearly so great. And so that's the main interest in 244. The other interest in 244 is that's not, it's not really a naturally occurring species at any measurable level to speak of terrestrially. So if you use it as a tracer, your uncertainty is going to be much lower than it would be if you use something else.
Just curious, what is
Oh, this was an underwing pod that had for aerial collections that had some of our devices on it. that we produce collectors that range from being as small as your hand to, you know, half the size of this table maybe, depending what it is. What I'd say about these collectors is that we do the design, the fabrication, the shaking it out in perfection, and then we fabricate the end products all the way through the cycle. We have design engineers, we have machinists, electrical engineers, electrical technicians to build. We build boards. We do all of that in-house in our organization. Yes, sir.
Glenn, the students that would like to do a summer internship with you this summer, is it still open, and do they just go to your website to?
Yes, yes. If you go to the SRNL website, there's a tab for employment opportunities, and that will allow them. There will be an ad in there both for postdoctoral positions, and I don't think the ad for the internships is up yet, is it, David? I don't think it usually doesn't go up till about Christmas time, but you can put those in. The postdoctoral one is already out there because we have a rotating one where we've got positions out there, and what we usually do is put some descriptions of the kinds of postdoctoral positions that people were looking for at this time. But yes, you can get on the external website, and if folks have any questions, of course, I left my card with Professor Ivanov and others, and folks are always welcome to send us an email, and we'll try to answer their questions as best we can.
A follow-up question: do you take foreign nationals for your internships?
Have we had any foreign nationals? I don't think so.
So it's a good question.
That is. I'm not sure.
You know, historically, the work in our programs has been inside the limited area, classified programs, and we've really restricted foreign national access. I would say that, and I think we talked about this several times today. Our challenge is to separate the basic science from its ultimate application, and when you do that, you free up the ability to work in an unclassified environment or unclassified scope, and then that opens up freedom for foreign nationals to do the R&D. So I think to answer your question in a less than specific answer, it's an area that we probably need to grow into a bit. And historically, it's not been an ability we've had.
Other questions? Okay, let's thank our
Thank you. Oh, thank you very much.
It was very good.
Was
So
it-
do you have card?
Oh, yeah.
We didn't exchange yesterday.
Oh, yes, I have a card. I suppose this needs to turn off somehow. We really appreciate you guys coming to talk with us. We're hoping that we can get together I think
Hello there, Lisa Marshall.
glad to meet you.
Nice to meet you as well. Oh, yes. You're very welcome. Any cuisine preferences? Any time?
Okay.